Okay, welcome to lecture here. We're going to pick up, I think, chapter 8, which is acid and bases. And as we talked about last time, we will, as I keep scribbling on the screen there, we will stop lecture a little bit early. Then the quiz will become available a little bit after 6. That way you can take it. And then if you have lab, obviously get to lab, and discussion if you get to discussion. So a little bit of lecturing, we'll stop, and then we will do the quiz after we stop lecturing here. Okay. Wow, I'm just like scribbling all over the place here, huh? All right. Let's try that again here, maybe. Okay, so we are into chapter 8, which should be acid and bases. As we talked about, I think last time, this is our sort of final chapter that will sort of have really calculations before we get into organic and sort of biochemistry, where it's more sort of memorization and that type of stuff rather than kind of calculations. And as I might have mentioned, you pretty much won't need your calculator for any of those chapters. So that's sometimes a good thing for people, maybe not a good thing. But sometimes people like maybe this part a little bit better as soon as we get done with this chapter. But this chapter does have a good number of calculations still to go, and we will have to learn a few more calculations before this chapter is over. Yeah, so in terms of the quiz, we will stop lecture early. We'll end this meeting, and then you could go to Canvas like normal and take your quiz. Yeah. And then afterwards, you could then go to whatever you have next, either lab or discussion afterwards. So yeah, so you don't have to be still logged into here. We'll stop the meeting. You'll get an announcement, and then you could go and take the quiz on Canvas using Proctorial, and then you can, like I said, continue on to whatever you have next. All right. So let's talk about acids and bases, which is what this chapter is about. So acids, they have sour taste. They cause changes in what's referred to as litmus paper. So typically, if you have litmus paper and it ends up turning red, that usually indicates an acidic type solution. And typically, acids can react with metals in a single replacement reaction. So, for example, I think we saw when we were talking about reactions, you do a little zinc with hydrochloric acid, which is HCl. It will make some zinc chloride and produce some hydrogen gas. So if you've seen that sort of reaction occur, there's a lot of bubbles and stuff that occur, and that's a result of really a single replacement reaction where hydrogen gets displaced and it comes out as elemental form of hydrogen, which is hydrogen gas. Acids can be strong electrolytes and are weak electrolytes and weak acids, which means, again, that they do have the ability to conduct electricity in that sense. Bases, on the other hand, they have a bitter taste. Obviously, you shouldn't taste any acid or base, but they do have a bitter taste. A lot of soaps, kind of drain cleaners, those type of things, those are bases. It also, when you use some type of piece of litmus paper, typically if that litmus paper turns blue, it is a basic type solution. And just like acids, we could have some strong bases, and we could also have some weak bases, which are also electrolytes. Again, electrolyte, as we talked about in last chapter, something that will basically produce some ions in solution. Those ions help complete the circuit and all that good stuff and help conduct electricity. So let's talk a little bit about some of the definitions of really what an acid or a base is. So starting with an acid is basically a substance that will produce H plus ions in solution. H plus is sometimes referred to in acid-base chemistry as a proton, and that's because hydrogen has a proton and one electron and no neutrons. So when it becomes positively charged, it loses its electron and it's left with obviously just a proton. The other sort of one that you see very often is H3O+. H3O+ is what is known as the hydronium ion. It's a polyatomic ion. And H3O plus and H plus are pretty much used interchangeable in acid-base chemistry. So that's both in sort of equations and reactions, and also in terms of formulas. I personally will use H plus probably everywhere. It's just what I use. Anywhere I kind of put H plus, you could replace it with H3O plus, again, in both equations and also formulas that we'll see. So again, it is definitely used interchangeable. H plus, H3O plus, basically the acid part of a solution. Strong acids are strong electrolytes, which means that they 100% break apart into ions. They do not stay together. Here are some examples of some strong acids. That's hydrochloric acid, that is nitric acid, that is sulfuric acid. A couple of other sort of strong acids is HClO4, that is perchloric acid. HBr is hydrobromic acid, and HI is hydroiodic acid. So these are some strong acids. And that means when you take something like hydrochloric acid and it is in solution, it will be like a strong electrolyte and 100% break apart into the ions, which is H plus and Cl minus. So in solution, you 100% have these ions. You have none of these strong acid units still together, much like a strong electrolyte. And this is why it's considered really a strong acid, because when it goes for a swim, it produces a lot of free H plus. And that is the key for something to really be an acid, is its ability to form free H plus ions floating around in the solution, or H3O plus. Again, they're both sort of interchangeable. But that production of that is what makes something an acid. And something that's a strong acid, because it 100% breaks apart, will produce a lot of free H plus very quickly. And a little bit different is a base. A base, sort of a basic definition of a base is something that will produce hydroxide ions in solution. So again, here the production of OH minus, which is hydroxide, in solution is what makes something a base. A lot of strong bases are also, again, strong electrolytes, which means they 100% break apart. But a lot of strong bases will have hydroxide actually in the formula, like sodium hydroxide, potassium hydroxide. These are examples of strong bases. If you look on your periodic table there, in group 1 and group 2, and if you remember what group 1 was called, group 1 is the alkali metals, group 2 is the alkaline earth metals. The word alkaline, that means basic. So a lot of our really strong bases come from group 1 and group 2 that has hydroxide in it. So for example, if you look on the periodic table, there's like sodium right about there. There's potassium. If you head over to like calcium and barium. So any of these sort of elements in group 1 and 2 that has like hydroxide in it are typically where a lot of our strong bases come from. And same idea here. When we have something like sodium hydroxide, when it's in solution, it makes Na plus. Not sure why it's an equal sign there. I forgot to hit shift, I think. So Na plus and OH minus. And just like our strong acid, 100% of what you have in solution when you have a strong acid are those ions. You no longer have any of the sodium hydroxide units still together. So you got really none of these guys still in that solution. And again, what makes it a really strong acid is the ability, like we can see here, to generate a lot of free OH minus. So that production of a lot of free OH minus really quickly makes something a strong base, just like a strong acid is something that can really produce a lot of H plus really quickly. As we will see, though, not all bases do have to have hydroxide in the formula, but definitely a lot of strong bases have OH in the actual formula itself. Any questions on that there? So what happens when we react a strong acid and a strong base together? Whenever we react basically a strong acid plus a strong base, we always get the same thing. We always get basically a salt plus water. A salt is an ionic compound. And H2O obviously is water. So for example, if I took hydrochloric acid and reacted it with sodium hydroxide, it is really going to be a double displacement reaction, positive, negative guy, positive, negative. It is always the H from the acid and the OH there from the base in the situation. If you just add that up, that's 2 hydrogens and an oxygen. That is where our water comes from. So the H plus from the acid, the OH minus from the base gives us our water. And the other part of it comes together to make our salt. So sodium that has a +1 and chlorine that has a -1 comes together to make sodium chloride. So this is our water and our salt here. So always what comes together is the H plus from the acid, OH minus from the base when we take a strong acid and strong base. And this is sometimes called a neutralization reaction, is because really the main thing that is actually being formed is water. So ultimately, if you sort of broke down any combination of a strong acid with a strong base, and you really sort of got to the heart of the reaction that's taking place, is actually just the formation of water. That's essentially what's happening here. And again, that is why it is sometimes referred to as a neutralization reaction. Now we can look at perhaps another type of acid. Here's that example that I wrote up there. We don't have to worry about spectator ions or any of those things on here. Here's another couple of examples of some strong acids and strong bases reacting together. This is nitric acid reacting with potassium hydroxide. This is positive, negative, positive, negative. Again, the H from the acid, the OH from the base gives us our water. And then the other two parts come together. That is potassium and that is nitrate coming together. And again, just like we talked about with naming, +1, -1 gives us our salt here, which is potassium nitrate. Now, in a lot of cases, the salt is going to be aqueous. Could potentially not be, but it really is. Now, there are some acids that are what are referred to as diprotic acids, like H2SO4, that is sulfuric acid. If I take sulfuric acid and react it with sodium hydroxide, same situation is going to happen here. It's going to be the H from the acid, the OH from the base, going to make my water. And now, though, when we put this together, we do have to think about, like we do with naming, this is actually sulfate, which is -2, and this is sodium, which is +1. So normally when we put something that is positive and negative together, we always want no charge. So like we did with naming, the correct formula here would be Na2SO4, which is sodium sulfate. And obviously we would need to do a little bit of balancing here to probably get it all correct here in that case. This acid here, which has 2 hydrogens, as we will see, is what is sometimes referred to as a diprotic acid. It means it pretty much has 2 H pluses to give. They actually do come off one at a time. And that is different than both of these acids here. These acids here only have 1 H plus in them. And these are sometimes referred to as monoprotic acids. Mono meaning 1, so it basically has got 1 H plus to give. So when you kind of write these things, these are really double displacement reactions. Those are really the two things that you typically get when you take a strong acid and strong base together. The water and the salt. So basically you literally can put your hand over the H in the acid, put your other hand over the OH in the base, and that's going to make your water. And then the two things left over, you just want to put them together correctly, like we did with nomenclature, and you will get the salt part from that. Question on that there. Okay. So let's talk about some early definition of acids and bases, and one was done by Arrhenius here. He did a lot of work with electrolytes. Electrolytes, as we've talked about, are again those things that break apart into solution, produce ions, able to conduct electricity. And basically, he defined an acid as something that is able to produce H plus in solution, and a base as something that's able to produce OH minus in solution. And that's why when we talk about sort of solutions here and we write formulas for acids, for example, HCl, you typically will see this aqueous symbol next to acids. And as we talked about with reactions, that basically means a water environment. And that's why we would call this hydrochloric acid. Now, that's different than if you had just HCl that's, say, in the gas form. This is not an acid in the gas form. This would be known as hydrogen chloride gas. But when you take something like hydrogen chloride gas and you sort of bubble it with some water, you actually will get hydrochloric acid here, and this will be formed. So it is very common that, we oftentimes can recognize an acid if it's not sort of explicitly said with that aqueous symbol next to it with something that has that H plus that makes an acid. So this was a very good sort of step in terms of acid and base sort of definitions. It was sort of limited because he did a lot of work with electrolytes, and he did a lot of work with bases that really only contained hydroxide in it. So he did a lot of work with bases that contain hydroxide. And that led us to sort of a more generic definition of an acid and base. And this, by the way, is sort of how we get something like our strong acids and base. Again, if you take something like hydrogen chloride gas, not an acid yet, until you put it in some water, and that's when we're able to liberate that free H plus and make it an acid at that point. And again, you can see it goes from a gas symbol to an aqueous symbol. Same thing with our sodium hydroxide, not really a base yet in the solid form until we dissolve it in water. And the important part here is it's able to, as we talked about, liberate that hydroxide and again be considered really a base. So these were really good sort of definitions of acid and bases, but again, it was sort of limited. So a more general definition of an acid and a base was one that was put together by Bronsted-Lowry. And the Bronsted-Lowry definition of an acid and a base is one that we could sort of apply to sort of all kinds of bases, also acids as well. And it's more of a definition about H plus and how that is basically moved around. So when we talk about the Bronsted-Lowry definition, a acid is a proton donor. So an acid is something that will donate a proton, so give away an H. But the important part is also on this, the positive here. So it's not just the H, but it is the positive charge that goes with it. That affects the charge, while a base is something that will accept the proton. So this is oftentimes what we think about when we think about acids and bases, is this Bronsted-Lowry definition, where an acid is something that basically will donate its H plus, and usually it's donating its H plus to the base that will accept the H plus, again going to affect the charge on each of those guys as that H plus goes from one place basically to the next. So to look at sort of the generic reaction of this is HA here, if this is an acid, and that is oftentimes used as sort of a generic formula for an acid. What's going to happen here is this acid is going to donate its H plus over to water, which means water will accept the H plus and act as a base in this case. And part of the sort of consequence of the Bronsted-Lowry definition is when this occurs, we actually get partners on the other side of the reaction. So the acid on this side is related to our A minus on the other side of the reaction. And if this is the acid, our A minus over here is what's considered the conjugate base. While if we look at water, water on the left-hand side is related to H3O plus on the right-hand side. And since water is a base, its partner on the other side is what is known as the conjugate acid. So we get this sort of acid conjugate base pair and base conjugate acid pair. And just so we're clear on sort of the locations of those things, the acid and base, just a regular old acid and base, are always on the reactant side. Our conjugate partners are always on the product side. Now, they are related to each other by a really important difference, and that difference is this guy right here. That difference is 1H plus, and 1H plus only can be the difference. So when we go from the acid to the conjugate base, it is 1H plus less. When we go from the base to the conjugate acid, it is 1H plus more. And that is an important relationship. In order for those things to be related to each other, that is the only difference that there can be. It can only be that 1H plus difference. So again, acid is something that will give away an H plus. The base is something that will accept the H plus. And what they do is they create basically partners on the other side where the difference is just that 1H plus. And again, that's an important sort of relationship there. Question on that relationship. Okay. And underneath that is what I scribbled already. So let's take a little bit closer look at this. Again, if we look at some real sort of acids and bases here, in this case, we have hydrochloric acid, which is going to be our acid. Again, here it's going to donate the H plus over to water, which in this case is going to be the base. And if you just think about HCl, basically if it donated an H plus, we get rid of the H and it becomes one more negative. So its partner again on the other side is right here, and that would be our conjugate base. While the base here at water will accept the H plus, and its partner on their side will become H3O plus, which is our conjugate acid. So again, if you just think about water being the base plus an H plus, you just add all those things together, that gives you 3 H's, an O, and a plus. So that is, again, what is formed basically over here. And again, the only difference between our acid on the left-hand side and our conjugate base on the right-hand side is 1H plus. Again, it has 1H plus less. And our only difference between the water, which is acting as the base, and the H3O plus is 1H plus more. So again, always when you're trying to find acid conjugate base pairs, 1H plus difference is the only thing that you should have. Question on that there. Okay. And here's just sort of the Lewis structure drawing of what's happening here. Again, basically our acid or our HCl, this bond right here is going to break. It is then going to send its H plus over, creating our hydronium ion and our chloride ion. And again, that's our acid, our base. And again, our partners on the other side are conjugate base and our conjugate acid in this particular case. Again, these two guys related, and these two guys related by that 1H plus difference. Any questions on that there? All right, so why don't you take a look at this next one here, and what you want to try to do is identify which ones are conjugate acid base pairs. So which ones of these next ones here are related to each other. And again, what we're looking for is only a 1H plus difference. So which one of these guys, 1, 2, 3, 4, or all of them could be pairs or not pairs. So take a minute here and try to decide. Okay, so let's take a look. So remember that what we're looking for here is just that one H plus difference. So that means however you want to look at it, either somebody gained the H plus, somebody lost the H plus. So when we look at these two guys here, HClO4 and ClO4 minus, these two guys, the only difference between them is one H plus. So you could either think about taking away the H, and when you take away the plus, you become one more negative. Or you could think about putting the H plus onto this guy, and you'll end up with the HClO4. So again, these guys are related to each other by just one H plus, which would make a conjugate acid-base pair. Second one is HCl and ClO minus. The difference between these two is one H plus, but there's also a difference of an oxygen. This guy doesn't have an oxygen. This one does. So it's a difference of one H plus and an oxygen, which means these guys would not be related to each other. So again, the only difference there could be is just that one H plus. So this guy would not be so good. Looking at number 3, we have H2PO4 minus. We have HPO4 2 minus. And again, you could approach it whichever way you want. You could either, take the H off. So for example, if we took the H off, we get rid of one of those hydrogens. And again, when we take the plus off, we become one more negative. So that's HPO42 negative, which matches. Or again, you could throw the H plus back onto this guy if you want to look at it that way. When I do that, I get two H's, a PO4 minus 2, and plus 1 gives me minus 1. So these guys are related to each other. Again, you could look at it either way, whichever is easiest for you. And that leaves us number 4 there, which is HNO3 and NO3 minus. Again, these guys are related to each other. Again, you can slap the H plus onto this guy and you will get this guy. Or if you take the H plus off, you will get the NO3 minus. So it looks like in this particular case, 1, 3, and 4 are pairs. Any questions on any of those there? Okay. So why don't you try these here? We want to write the conjugate base for each of these. So for each of these guys, write what you think the conjugate base should be. So take a minute or so and try to come up with it. Okay, so when you got something like this, where you're asked to write the conjugate base, sometimes it's good to sort of think about where these things came from. So what I mean by that is we saw the relationship here with the Bronsted-Lowry of on the reactant side, we have an acid and a base, and on the product side, we have the conjugate acid and the conjugate base. And again, the relationship, as we talked about, is if it's an acid on the left-hand side, its partner will be the conjugate base. And if it's a base on the left-hand side, its partner there will be the conjugate acid. So really the key is I need to do something with an H plus. I need to decide, should I put it on or should I take it off? And what's going to allow you to determine that is sometimes it's helpful to think backwards, which means if they want me to write the formula of a conjugate base, that means if I work myself backwards here, what I am looking at and what I am starting with is an acid. And the definition of an acid is something that will donate the H plus. So what that tells me here is I want to actually take away an H plus from each of these, because in each of these cases, these things should be acids. So using that sort of thought process there, starting with H2S, I basically need to get rid of an H plus. So when I get rid of a 1H, I am left with an H and an S. And again, when you get rid of the plus, you become one more negative. So this would be HS negative. Now, when I get to here at HS negative, again, as I already determined, this is an acid as well. I'm going to take away the H, which will leave me an S. And again, when I take away the plus part of it, I become one more negative. So I go from -1 to -2. So S2 minus. Same approach here. Again, we're assuming this is an acid in this case. So we want to get rid of an H. So NH2. Again, there's no charge here, but when I get rid of that positive charge, I become one more negative, and it would be NH2 minus in this particular case. And lastly here, assuming this again is an acid, we're going to get rid of the H. So that's going to give us one H, an S, an O, a 3. Same deal here. No charge becomes one more negative and ends up at -1 there, HSO3. Again, both of these guys are related to each other by the difference of just one H plus. Any questions on those there? So let's say we had something like HCO3 minus. Could you write the conjugate acid for it and write the conjugate base for it? So see what you come up with. So what is the conjugate base for this guy and what is the conjugate acid for this guy? Okay, so let's take a look. So same idea here. Really, the choice is we got to do something with the H plus. So again, either we're going to put it on or take it off. So why don't we start with the conjugate acid? So if you're asked to write the conjugate acid for this guy, again, you want to think about it sort of backwards. So if I'm asked to write the conjugate acid, the partner on the other side is a base, and the definition of a base is something that will accept the H plus. So in this case, I would actually put the H plus on, and that would give me H2CO3. When I add one H to this, I get H2 plus 1 minus 1 gives me 0 in terms of the charge that's going on there. Now, just like we did with the examples here in this problem, if I wanted to write the conjugate base for this, that again means if I work backwards, like we talked about previously, I would then be dealing with this as an acid. And that means that I should donate the H plus like an acid would do. And when we take the H plus off, it would be 1 carbon, 3 oxygens, minus 1 then will become -2, and we get carbonate. Now, this guy right here, as you can see in this example, in certain cases can act as an acid, and in certain cases can act as a base. And that oftentimes happens when you have hydrogen on something and something with a charge. You oftentimes have something that could act either as an acid or base, and that is something that is known as being amphoteric. It's a substance that could act as an acid or a base. So again, something like that where you have the H and a charge typically has the ability to do that. Water, as we will see, also has the ability to do that, act as an acid or a base. Question on Bronsted-Lowry, acid, bases, conjugate bases. Again, main take home from this is 1H plus only is the difference. Regular acid and bases found on the reactant side of the arrow. Conjugate acids, conjugate bases found on the product side of the reaction. Any questions on that? Okay, so I think that's a good place to stop. So we will stop here. Again, the quiz will open up probably in about 10 minutes, and you'll have about 25 minutes, I think, to take the quiz. I ended up writing it, so you will have to upload some work this time. So you will need a piece of paper to kind of like the exam, work out some of the steps and upload it after you submit the quiz. So again, you go through the quiz. Once you start it, you can't stop it. Hit the submit button just once. And online there, just give numbers for answers. Don't put any units online, but on your paper that you're going to upload, make sure you put the units and stuff like that. So for the answer boxes online, just make sure that you only do numbers, no units. I think there's 3 questions, to be honest with you. So I think there's only 3 questions. So once you submit the quiz, like the exam, you need to immediately upload your work. And once you submit the quiz, in that module on the bottom, there will be that spot where you can upload your work. Yeah, so make sure that you do that immediately there after you submit the quiz. So just kind of like the quiz we took before and also the exam, there'll be a module that will open up and you'll have that honesty agreement. Then that should open up the quiz. You could submit the quiz and then that will open up the thing for you to upload your work, and then you'll be done with the quiz part of it. So you have 25 minutes. If you take it when it opens around 6:20-ish, 6:30 the latest, you will not run out of time. Again, if you take it too late, the computer will cut you off and it will not be reopened for you. I think everything should be pretty self-explanatory. I didn't give you a periodic table because honestly, you don't need one. So there's no periodic table. Don't look for one. You actually don't need one for anything. You can use a calculator, obviously. You can use paper to work up the work and upload it. Again, make sure you show all the steps, the units and all that stuff on the work you upload. And obviously no notes, books, people, all that good stuff. Yes. So make sure you go in through the proctoral like we've been doing. And again, if you take it around when it opens in about 10 minutes or so, you should be fine. You won't run out of time. But again, if you start too late, you get whatever time is left. Again, if you take it when it opens, that should give you plenty of time to take the quiz, upload your work, and then obviously get to lab if you have lab, or obviously discussion if you have discussion. A couple of other reminders. Next week, a week from today, is our next exam. Again, that covers, as we talked about last time, chapters 5, 6, and 7. And like we did last time, we'll just take it on Wednesday during lecture time, and you'll have the entire lecture time to take it. And then obviously you can go to lab afterwards or discussion afterwards, depending on which one you have on that day. Any questions on any of that stuff? Okay, I think it should be pretty self-explanatory. There's some constants, some conversions on the first question. It's not really a question, it's just the constants and conversions, like R values and stuff like that. So you should have that available to you as well. And if you do have questions on something or have problems, please email me immediately. So hopefully you won't have problems, but at least I could hopefully answer it and stuff like that. Other than that, if you have lab afterwards, have a nice weekend and all that good stuff. We will obviously continue lecturing here on chapter 8 on Monday. Again, a reminder, quiz and exam next week. And that means homework as well is due. And if you have discussion, we'll start discussion. We'll start discussion about 7:10, just give you a little chance to maybe stretch if you have discussion. That way, in case you do have any questions, I'll be happy to answer them. All right, other than that, make sure you put here. And like I said, if you're off for the weekend, have a nice weekend. And good luck on your quiz. And I'll see those that have discussion. Again, we'll start about 7:10.